Okay, it's 2:30, so let's get started. The first part of this class will be about this problem called the all pairs shortest path, and then we'll transition into a completely new topic. Okay. So the all pairs shortest path is kind of like the single source shortest path, except it says I want the shortest path distances between all pairs. Okay. So it's kind of like I want all the nodes to be sources, and then I want the distances from every node to everywhere else. Okay. Previously, in the single source shortest path case, the source was fixed. Okay. So if I ask you to solve this problem, there's kind of the most natural, and then this graph is directed, whatever the edge weights can be negative, right? The most obvious thing to do is you just run Bellman-Ford from every node. Okay. So Bellman-Ford, if you recall, was this algorithm, that if I told you a source, it found the single source shortest path, from that node to all the other nodes in the graph, and the graph could have negative edges, So if you run, Bellman-Ford from every vertex as a source, then you get this O of V kind of on top, So you get V squared E. Except, it turns out because you're solving this all pairs problem, you can actually do a little bit better, okay? So this class is going to be about a different algorithm, which is kind of like instead you're going to do Dijkstra's O of V times, okay? So of course, you can compare, Somehow you have this V squared times E term, but that becomes a VE term, okay? But of course, we can't do Dijkstra's from every node because the graph could have negative edges, okay? So this is sort of like an imaginary hypothetical runtime if we could run Dijkstra's from every node, okay? It's like the Dijkstra's running time multiplied by V, okay? So actually what it turns out is if I want to solve the all pairs shortest path problem, you can essentially get this running time, okay? Even though the graph may have negative edges. Okay, so that's going to be the first part of this class. An algorithm that's sort of pretending that the graph was positive edges. So yeah, so the algorithm is called, so it's very short, so I'm going to just do it on the board. It's called Johnson's algorithm, okay? And essentially the power of Johnson's algorithm is somehow if we know that we want to solve this all pairs problem, we're going to kind of process the graph so that it ends up having only positive edges, even though it's started with negative edges, okay? And then I can pretend to do Dijkstra's n times, okay, where n is the number of nodes. Okay, so that's what Johnson's algorithm is going to be doing. But first, so Johnson's algorithm has roughly 3 steps, okay? One is we're going to, so we have this graph, graph G. The first step is what I'm going to say is somehow I'm going to find some magical numbers, okay? And I'm going to have it 1 for every node, okay, in the graph. So I'm going to find n magical numbers with the following property, okay? If I take any edge in the graph and I add the magical number from U and I subtract the magical number from V, it ends up being positive, okay? So the first step, I haven't told you how to find these magical numbers, but the first step is to find these numbers, okay? And essentially what I'm doing is I'm finding some ways to transform the graph by adding some values and subtracting some values so that the resulting edges end up being positive, even though the initial edges could be negative, okay? So that's the first step. The second step is, well, if I'm going to define this as W sub h of UV. So I'm going to change the edges somehow so they become positive. Then if my graph is positive, then I can just run Dijkstra's from every node, okay? That's the second step, run Dijkstra. Okay. Whatever, from every node. I don't know the spelling. Okay, that's the step 2, If I can somehow transform the graph to have positive edges, then of course I can run Dijkstra's from every node, and that will give me this running time, which is Dijkstra's running time times V, okay? And then somehow the last step, okay, step 3, is to go back to the original graph, okay? Go back. Okay, that's the last step. All right, so Johnson's algorithm has 3 steps. First, like I said, transform the graph so it's positive. Then if it's, off all the edge weights are non-negative, right, then I can run Dijkstra's from every node, and then I have to go back, okay? That's the high-level plan, okay? Does that make sense? Right, and like, why are we doing this? Well, the point is, like, then I can take advantage of the fact that Dijkstra's runs faster than Bellman-Ford, right? But the thing is, I can't. It turns out I can only do this number 1 step. It's going to be a little bit costly, so I cannot do it for the single source problem. It's going to be a little bit too costly for that. But because I'm running all pairs, right, I have enough running time. I have enough like leeway to run this magical step 1. Okay, all right, yeah, yeah. So I haven't told you how to do it, but the first step is the following. Okay. Somehow I'm going to find for every node in the graph, okay, a magical number, okay, such that I'm going to transform the edges. I'll draw an example. And how am I going to transform the edges? I'm going to take the original edge. I'm going to add the number on one endpoint and subtract the number on the other endpoint, okay? So I'm going to have n numbers, right, 1 for every node. And that's going to allow me to transform every edge, right? I take the original edge, I add something, I subtract something. And I want it to be such that after this transformation, the edge becomes positive, okay? And the claim is, right, I mean, of course, I haven't told you how to find it or if these things even exist, right? But somehow, like, if we can find this, right, then the graph becomes positive. Then I can run Dijkstra's, right, which is much faster than Bellman-Ford from every node. And then somehow I want to go back, okay? And if you, if you have, like, if you ever, if you're also physics major, right? This is like adding potential to the endpoints, okay? So adding these vertex potential to every endpoint, okay? All right, and like I don't know if it's like Ohm's law or whatever, but it's sort of similar, okay? And actually, I think one of these people, Dijkstra or Johnson, was actually from, like, they weren't computer scientists. They were from physics, I think. Okay. Okay, cool. So now let's proceed with the plan. So let me just draw you an example, okay, of like what this plan looks like on a concrete graph, okay? But essentially, the magic is like I can transform a graph with negative edges to like one with positive edges somehow, okay? So let me draw an example, okay? That's one node, another node, another node, another node. Let's say this is 6, 3, minus 7. And this is, let's say, 2. This is 4. This is minus 3, okay? Okay. So this is clearly a graph with the negative edges. So I claim the following magical numbers work, okay? So the number for W will be minus 1. Number for X would be minus 7. Number for Y will be minus 4. Number for Z will be 0, okay? Right? And we'll talk later about how to get these numbers, but I'm just going to tell you these are the numbers, okay? And now what I'm going to do, I'm going to transform on every edge, okay? So for this edge, I'm going to I'm going to add this one and subtract this one, okay? So then this is going to be, right, if I add minus 7, that's minus 1. Subtract minus 1, that'll be 0, right? It's going to be 0, okay? And if I do this for all the nodes, okay, then this ends up being, right? So let's do it again, right? I add W, that's minus 1. I subtract 0, right? So that's 1. So essentially, we're going to end up with this graph, okay? 1, 1, okay? So you can kind of do this on your own. But the nice property is, because you're only adding and subtracting at the endpoints, this is going to preserve all the shortest paths in the graph, okay? And I'll prove it in a bit. But the idea is, right, in a path, kind of because you're adding and subtracting, all the intermediate things will cancel, right? This is called telescoping. So then somehow if I can find these magical numbers, then it preserves the identity of the shortest paths. Okay? All right? Does this example make sense? So like for instance, right, well, we'll prove it, but right, I had this graph, I found these numbers, and somehow they transformed all the edges to be positive. Okay? Okay. So now let's prove the following, okay? Which is, let's start with step 3, right? I want to show that the shortest path in this transformed graph is the same as the shortest path in the original graph. Okay? That's what I want to show. And you can kind of see it here. Okay? So here the shortest path from, let's say, W to Y was to go through here, right? It was like, is that right? That was correctly. Oh, sorry, there was one other edge too here that I had before. Oh yeah, 5, which also became 1. Yeah, previously, right, let's say you want to go from W to Y. Then in the transform graph, it's like you do one step, that's 2. And in the original graph, you can also check that was the fastest way, okay? Anyways, I think the proof will be pretty illuminating, so let's just kind of draw it out, okay? So, okay. But yeah, this, well, this is just one example, okay? So let's just see. So why does doing this transformation like preserve the identity of the shortest path? Basically, just imagine, right? I have some node U, and I have some path to some node V, right? In the graph that you started with, and let me just draw. You know, let's say it had 4 nodes in the path, okay? Right? So previously, right, it had some weight, right? This path had some weight, which is the sum of these 3 edges. But now what am I doing, right? Well, what is the vertex potential, right? I'm adding this, so adding U, right? And let's call it X and Y. I'm subtracting X right here, right? Subtracting X for this edge. Here I'm adding X and subtracting Y, right, for this edge. Here I'm adding Y and subtracting V for this edge, okay? So then if I say, okay, the weight of the old path is something, right? Then the weight of the new is, right, if I sum across the new weights, all these intermediate things cancel, right? Because I'm adding on one side and subtracting on the other, right? Right, when I go from an edge, right, this edge to this edge, right, I added X here, I added X here, right, but I subtracted X here. So the intermediate things cancel, yeah. Yeah, so let's, okay, let me write it out in more detail. Yeah, so let's just write a proof, okay? Let me erase this here. Okay. Right. Okay. So just write the full proof, okay? Okay. So consider some path, okay? So it starts from V0, goes to V1, goes to V2, blah, 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 goes to Vk, okay? All right, consider this path, okay? Just any path. I want to show that somehow the weight of the path is the same, except you're shifting by the same numbers, okay? So what is the weight of the path in the new graph, right? What is the weight of this path? Well, it's the sum of all the weights, right? So the sum of all the weights, right? Weight from Vi in the new graph, right? With the new edges, Vi plus 1, right? Right, that's by definition, right? But what is the new weight? Well, the new weight is, right, the old weight, right, of this edge, except, right, I have to add the vertex number at one endpoint and subtract the vertex number at the other endpoint, right? Right? So I'm saying for every edge, right, the new weight is the same as before, but I add this number and I subtract this number. But now I'm summing across the path, right? So that means right here, right, I subtracted v1, right? But here I get to add v1. Here I subtracted, so here I subtracted v2, right, for this edge. But here I get to add v2. So all this is saying is, if I write the sum, right, well, I get the old weights, right, sum over the old weights, w old. But this is a sum that is, right, this is called telescoping, right? Right? For one term, you get a plus. For the very next term, you get the minus, right? Does that make sense? So let me give you some concrete numbers, okay? So all I'm saying is, right, let's just say I have this path, right? And the number here was, the number here was 3, number here was 4, number here was 5, number here was -7, okay? I'm just making something up. But for now, this edge, right, it gets a +3, -4. For this edge, it gets a +4, -5. For this edge, right, it gets a +5, -7, right, +7. So kind of all these intermediate things cancel, right? That's all this is saying. Okay. So what that means is the weight of the path in the new graph is the same as the weight of the old path plus the potential at the endpoints. Okay. Potential at the endpoints, right? So right, there's two terms that didn't cancel, which is the potential at one endpoint minus the potential at the other endpoint, right? These magical numbers. But this is like the same value for every path, right, that goes from this endpoint to the other endpoint. So that means the identity of the shortest path is the same. Okay? So all I'm doing is like just raising all the values of the paths from, let's say, from one node to the other by the same number. So of course, the smallest one remains the smallest, right? Okay, so that's all I'm doing. I'm just raising the value of all the paths by the same number. Okay? And the reason it's the same number is because all these intermediate, right, the paths could be of different lengths, right, different number of hops, but somehow all the size of the number of hops in the path cancels. Okay, the only thing that you're left with are the potential of the two endpoints. Okay, so what that means is, in this transformed graph, the identity of the shortest path is the same. Like the, whatever path was the shortest before remains the shortest. Okay. Does that make sense? Any questions? Yeah.
Why would you not just why don't you just add a constant number to each edge such that the even negative ones go all the way to positive?
Yeah. So you can't do that because paths could be of different hops, right? So you're adding different values here. Like if a path had 2 hops, you're adding, let's say the constant was 5 billion, you're adding 10 billion. But if the path was like 10 hops, you're adding like 50 billion, right? That's not true, right? Because the graph can have negative edges, right? So the size of that number of hops is not necessarily related to the length of the path, right? Yeah. So that's why you need to do this in this clever way where things cancel in the middle. So the only thing you're left with is the things at the endpoints, which are the same for every path, right, from one to endpoint. But yeah, that's a very good question, right? Like, how did someone come up with this? Probably the first thing they had was like, oh, what if I had this constant value? And they'll notice oh, that is sensitive to the number of hops. So then they came up with a way so that if instead of adding to all edges, I add to one and subtract from the other, the intermediate terms cancel. Okay. But yeah, that's probably whoever came up with this, that's probably the first thought that they had. So that's great. Okay. So far I haven't discussed the algorithm, right? I just told you if there is a way to find these magical numbers so that if I take an edge, I add something on one endpoint, subtract something on the other, and somehow they end up being positive, then I'm really happy because that allows me to use Dijkstra's algorithm. And clearly, like, nothing has changed. Like, the structure of the graph hasn't changed because the shortest path remained the shortest. Okay? All the paths are kind of lifted by the same value. Okay? All right. So that's kind of like the structural part. But the next thing is, okay, do these numbers even exist? How do I find these numbers, right? That's the, okay, so that's, so this is kind of like, right, remember there was 3 steps, right? The first step was find the magical numbers. Step 2 was like run Dijkstra's, and step 3 was go back. This is the part about going back, right? Essentially, it's saying going back is easy. It's just whatever the shortest path is, it remains the shortest path, okay? All right? So the more interesting thing is, okay, how do I know these numbers exist, and how can I find them, okay? All right. Yeah, any questions before we move on to that step? Like, feel free to ask, this is, it's a very cool idea, right? Somehow you're saying, I have a faster, right? This is just a general principle. I have a faster algorithm if the input has a specific structure. So I'm going to transform a general input to one that has a specific structure, right? So I can exploit that structure. And that's like a general, problem-solving strategy, right? Not just in algorithms, but just like, what's a good example? Like, it's a good example, right? Let's say, right, like you want to use a library that's only written in C++, but you only know Python, right? So what do? Right? You write whatever code you need in Python, and you use another code to transform your code into C++, right? So it's kind of like that, right? I know a special structure. If the graph has non-negative edges, I want to transform my arbitrary graph into one that has non-negative edges, okay? But I didn't tell you how to do it. I'm saying if these numbers existed, you could do it. Now the cool step is like showing that these numbers exist most of the time, okay? Okay. And I'll only show you like one side. The other side you can read from your notes. But the main theorem is, right, these numbers, h sub v, right, such that if I add one, for every edge I add one endpoint, subtract from the other, exist if and only if G has no negative cycles, okay? This marker is not working. But essentially, we're going to show that I'm going to give you a way to find these numbers, and that way is only going to work if if G has no negative cycles. And that kind of makes sense, right? You can't expect these numbers to exist for graphs that have negative cycles, because on a cycle, everything is canceling, right? So somehow you cannot go from negative to positive, because all these changes you did canceled on a cycle. But essentially, as long as the graph has no negative cycles, you can find these numbers, and you can transfer this graph into a positive graph, okay? And the way we're going to find these numbers is using Bellman-Ford, okay? So that's why you cannot do this for the single source case, because you're going to use one call to Bellman-Ford. So that's like already going to be very expensive, in the single source case. But you're only going to use it once, so that for this entire all pairs problem, right, you just did one round of Bellman-Ford rather than n rounds, okay? So that's the main theorem. Before we prove it, like, does everybody understand the theorem? Comments? Questions? Okay, so the way to find this is actually very clean. And it's the same idea as one of the problems in the homework, which is, right, I have this graph, G. The way I'm going to find these numbers is I'm going to add a new node to the graph, S, called the super node. I'm going to connect S to all the vertices in the graph, okay, with weight 0, okay? And then I'm going to use Bellman-Ford to find the shortest path from S to all the nodes, okay? And of course, that step will tell me if the graph has a negative cycle, okay? And at that point, I can say, okay, this cannot be done, okay? And the claim is that these magical numbers, h sub v, is just the distance, the shortest path distance from S to that node, okay? That's the claim, all right? So the claim is that if I add this new node connected to the rest of the graph in this way, then the distance from that node to all the other nodes are these magical numbers that I'm trying to find. And if I use those numbers and transform the original graph, the edges become positive. Okay, that's what we need to show. All right, but right, this step, right, finding the shortest paths from this new node to all the nodes, that requires Bellman-Ford, right? So you cannot beat the Bellman-Ford running time. Okay. I mean, so I need to prove this, but any questions about like what just happened? Yeah, first your question.
Just like arbitrarily connect S however you want?
No, you need to have an edge to all the nodes. Just in like, just add, kind of like imagine I'm just hanging it by like a thread, like I have this S connecting all the nodes. Okay. Yeah, sorry.
Okay, so like when you say that you're assigning each of V, that's the magical number, you're assigning to the shortest path from S to V, so V is like every single.
Yeah. For every, like, say, it says there's no number 1, right, in the original graph. What is the magical number for 1? It's going to be the distance from S to this node. Okay. And that distance could be the negative, okay, because the graph could have negative edges, right? Somehow it could go here and then do some random stuff and then get to 1, okay? Yeah, sorry. Yeah. No, for this proof, all the edges will be 0, okay?
But it has an edge to every single vertex, vertex. How does it, isn't just the path from S to any vertex 0?
No, because there could be, graph G has negative edges, right? So there could be a shorter path.
Oh.
Yeah. The whole point of what we're trying to do is this G is this bad graph, right? It has negative edges. I'm trying to transform it into something positive. And I'm going to do this like kind of a weird trick. But we're going to see that somehow this number will magically work. This number could be negative. Somehow it will magically work, okay? That's the cool part. And of course, right, if G has a negative cycle, right, this step will also find it, okay? The question is, why do these numbers work, okay? So let me kind of recap, okay, what has happened so far, okay? Let me recap what has happened so far. So far, I've kind of said, okay, I want to, if I have this graph G, right, I want to find a magical number for every node, right? Let's say there are n nodes. And the property that I want from these nodes is that if I kind of transform the edge, right, by taking the old weight, adding one endpoint, and subtracting the other endpoint, it becomes non-negative, okay? So I wanted to find a way to transform this. And then I showed that, right, if there's a way to do this, then sort of the identity of the shortest path remains the same, because every path from any node, like node 1 to node 17, they all get shifted by h1 minus h17, right? They all get shifted by the same value. So who is the shortest path stays the same. And the claim is that if the graph has no negative weight cycle, right, so that these distances are defined, otherwise it'll be like negative infinity, wouldn't make sense, then these numbers will work, okay? Then these numbers, if I plug those numbers in, for every edge, they will transform it into something positive. Okay, so why is that? Well, that's one line calculation, okay? So the proof goes like this, okay? Right? The shortest path from this S to some node U plus taking the edge from U to V has to be always larger than the shortest path from S to V, right? Because this is one possible way to get to V from S, right? You go to U and then U to V. Well, it's not going to be better than the best possible way. And then now what happens if I rearrange it, right? Well, this is HU. This is HV, right? And then I pull it on the one side, and you get not greater than or equal to 0. Okay? So that's the proof. You see, like now what I do is I just put this on this side, right? I get this minus HV greater than or equal to 0. Okay? So that's the entire proof. Okay? Just to recap, right? All I'm saying is the distance from S to U plus taking this edge U to V has to be at least bigger than, or not smaller than, distance from S to V, right? Because this is one way to get to V. Go to U first and then hop. This is the best way. And that's just like, that's just by definition, right? The best way can only be better than one way that I tell you. And then, right, that equation is the same as that equation, right? I'm just rearranging it now. Okay. So the entire algorithm, right? We kind of talked about the structure and why it works, but the entire algorithm is very simple. Okay. So this is the entire algorithm. Someone gives me a graph, right? It has negative edges and says, okay, find the shortest path from every node to every other node. Okay. That's the problem. How do I do that, right? Well, if somehow the graph was positive, had non-negative edges, I could just run Dijkstra from every node. That'd be very fast. I cannot do that because the graph has negative edges. So what I do is I spend one Bellman forward call to do the following. I add a new node. I connect it to all the nodes with weight 0. I find the distances from that node to all the nodes using Bellman forward. Somehow it will give me these magical numbers. I transform the graph. Then I do Dijkstras from every node to all nodes, right? I can do that. Now it's positive. That retains the identity of the shortest path and the distances, right? I just have to subtract. I just have to do like some twiddling at the end. And then I'm done, okay? So I find this cool because, like, right, somehow you're reusing information from across all the calls, right? Like, we could only afford to do this step, right? This already cost you one Bellman forward because I knew I was going to do a more expensive computation. So that's kind of a meta story in this kind of field, algorithm design, right? If you know you're doing a lot of work, you can save some of your computation to help you down the line. That's essentially the main. That's like a very cool way that it's being demonstrated here. Okay. Right, because naively, right, you just run Bellman forward from every node, but somehow people figured out that you can save computation like this. Okay. That's pretty cool. Yeah. Questions? Yeah.
So S is a node connected to all other nodes in G. So that could be like a new node that you're making just connected?
Yeah, exactly. Yeah. Just making up a new node. Yep. Making up a new node. Yeah.
So can you go back to your point of like why the new dot should every other original vertices? So sorry, have to have like the weight of 0.
Why is it 0? Well, I don't want to change anything in the graph, so that's kind of why you're adding 0. But in some sense, it doesn't really matter. All you need to do is check that these numbers work, okay, at the end of the day. And these numbers work just because going to V from S, one way to do that is go to U and then take this edge U to V. And that kind of like magically tells you that these the numbers work. But adding 0 is just one simplification, I guess. Yeah. Okay. All right. So this is the end of graph search. So now we're gonna move on to. There's still some stuff to talk about graphs, but this is the end. Okay. We're done with finding the shortest path. Okay. Any comments, questions? Okay. Right. If you didn't understand something, feel free to ask me. Happy to explain intuition or like what happened, why it works. Okay. All right then. So let's move on to a new topic. All right. Okay, so now we're done with graph search. Now we're going to kind of begin a new unit, I guess, called greedy algorithms. And this is going to be a bunch of examples where problems where doing greedy gives you the optimal solution. We've kind of seen examples of that, right? Like dynamic programming is kind of one example where you're just doing the greedy step, right? The best greedy step, and that gives you the globally optimal solution. Like Dijkstra's algorithm is also one example, right? Every point you're doing some like these relaxation-based algorithms, right? You're doing some local update at every step, but ends up giving you the globally optimal. And there are a bunch of examples. It's kind of hard to say like when you should use greedy algorithms, But in general, right, if you're faced with a problem, greedy algorithms tend to work somewhat okay all the time. Because you're using some structure, right? Like you're saying, what is the best choice at every step? And we're going to see some nice examples where greedy algorithms are actually the optimal algorithms, okay? Or like they will give you the best global solution, okay? All right, so now let's just get started. Yeah, like I said, right? I mean, it's hard to kind of classify what greedy algorithm really means because there's so many different examples. But essentially, it's one where we're making somehow locally best choices, but they, end up giving you the globally optimal solution. Okay. So the minimum spanning tree is one really nice example of how it works. All right. So let's just dive right in. Okay. So for now when I say minimum spanning tree, right, I give you a graph. The graph has weights on the edges, positive and the negatives, but there's no the direction on the edges, okay? So the edges are undirected. And I want to find a way to connect the graph, okay? So that's the spanning tree. So you can imagine like there are a bunch of homes, right? They're connected in all sorts of ways. There's also rows between them. I want to find the best, sort of the most concise way to connect them, okay? That's called a spanning tree of the smallest weight, okay? So here is one example, right? I give you a graph, okay? That's my input. It has weights on the edges. I want a way to connect all the nodes, right? If I want to connect all the nodes, then the best way is a tree, right? Tree kind of doesn't have any cycles, right? So you're not connecting things multiple ways. So a tree has a unique path, right? From every node to every other node, right? That's what makes it a tree. But I want the tree of the smallest weight, okay? All right, so that's the minimum spanning tree problem, right? Minimum because of the smallest weight, spanning tree because I want to connect all the nodes, okay? And this problem kind of shows up in many different areas. Like, I don't know, like if you want to, connect people to like cell towers, right? You're solving some version of this problem, okay? But at least does the problem make sense? We want the tree of minimum weight that connects all the nodes, okay? And the interesting thing about this problem is like, okay, there are so many possible trees, right? There's even exponentially many trees. So you can't hope to check all possible trees. So we need a much faster algorithm, right? I mean, you can't really, in polynomial time, you can't hope to check all possible trees, okay? Okay, so does the problem statement make sense? What we're trying to solve, okay. All right. Our minimum spanning tree is always like, there's only one. No, that's obviously not the case, right? You could have, imagine a graph where all the edge weights are the same. They're all 1, let's say. Then any spanning tree is a minimum spanning tree, right? Tree only has n-1 edges. But it turns out, right, actually, I won't prove this, but it's in the notes if you're interested. If the edges have unique values, then the tree is unique, it turns out. That's a nice fact, but not so important. All right, so what we're going to do is I'm going to show you some like special properties of minimum spanning trees. And then using those properties, we're going to build a greedy way to find the globally optimal tree, okay? So the first property is called, I guess, swapping the edges. And it says the following, okay? So there's a diagram, which I'll go through. But essentially it says, let's say I have some spanning tree connecting nodes, and I add an edge, okay? If I add an edge to a tree, it makes a loop, okay? Any tree, if I add an edge, make loops. And all it's saying is, well, if I add an edge, make a loop, and I remove some other edge in the loop, it's going to remain a spanning tree, okay? So imagine, right, so my graph is this, and let's say the spanning tree was this like two-sided edges, okay? So these was the spanning tree. Okay, this is a spanning tree. For now, don't worry about weights. And I'm saying, okay, what if I wanted to add this edge to the tree? It's no longer a tree now because it makes a loop. But it's saying, okay, as long as I remove any other edge in the loop, the tree remains spanning. It still connects everything, okay? And the proof is basically by picture, right? Like if let's say I added this edge and I remove this, I can still get to everywhere else in the tree, right? By kind of any path that went through F, or it just goes on the loop now and goes through E instead, okay? So all this is saying is if I have a spanning tree, I can add an edge, makes a loop. I remove something from the loop, the tree remains spanning, okay? That's the first property. Questions? So it's not saying anything too deep. It's just saying I can maintain a tree by adding one edge and deleting one edge. Okay. Right. So yeah. Any questions? Okay. So that's one property of spanning trees. Okay. So it's a simple property. Yeah. And then right, the formal statement is the following. Right. Let T be a spanning tree. Right. Let E be an edge that's not in the tree. If I add the edge, right, then it makes a loop. And if I remove anything else in the loop, the tree, right, the new thing is still a spanning tree, right? You can imagine, okay, I added something, I deleted something, maybe that disconnected the graph, but that's not going to be the case because you deleted something on the loop, okay? So like there's always, right, in a loop there's two ways to get to places, so you'll always maintain one way, okay? That's the main idea. We won't prove this, but the proof is this picture itself. Like I said, right, adding an edge makes a loop. I remove something in the loop. Okay. All right. So that's the first property of spanning trees. Somehow we can add and remove edges, keep it spanning. The second property is going to be called the cut property, which I'll get to in a bit. But first, what is a cut? Okay. So the point of a spanning tree is to connect the nodes, right? And kind of what prevents things from connecting? Well, what does it mean to connect things, right? Essentially, the idea is if I cut the graph into two pieces, like if I say, okay, all the vertices, these vertices go on one side, and these vertices go on the other side, okay, that's called a cut. So these two edges are the cut. And essentially what's going to happen is, right, any spanning tree has to cross the cut, right, because it's trying to connect vertices, right? If a spanning tree didn't cross the cut, it has, if there's a cut that the spanning tree didn't cross, then it can't connect vertices, right? So that's what we're getting at, okay? But a cut is just a way to partition the graph into two pieces, and like the pieces in between is called the cut, okay? All right. All right, so the main property that we're going to use of minimum spanning trees is if I consider any cut, right, any way to partition the nodes into two pieces, then the least weight edge crossing the cut is in some minimum spanning tree. Okay, so that's important, right? It's saying, right, let's say somehow I've connected most of the graph, and there's still a piece that's yet to be connected, right? That's a cut. Right? I want to go from the connected part to the disconnected part. How do I cross that, right? What edge do I add to the tree? Well, this is saying it's okay to add the smallest edge crossing this cut. It's okay to add the smallest edge that connects two pieces. That's always going to be a valid choice in the minimum spanning tree problem. And that kind of hints at what the greedy algorithm should be like, right? You're just adding these smallest crossing edges every time. We'll get to that in a bit. But this is like the key structural property of minimum spanning tree that we're going to exploit, okay? Right, and that's why, like, for greedy algorithms, you kind of need some structural property or special property, right? Like this, right? Somehow that hints at that, making a local step is not bad. Okay, so this is kind of the key thing for a minimum spanning tree. Okay. So pictorially, it's like this. Okay, so let's say I have a cut, right? Meaning I separated, the first three vertices and the bottom three vertices, and there are two edges, right, crossing this. I'm saying, okay, I can always pretend, or like I can always add this edge. Like this edge will always be part of the minimum spanning tree, okay? The smaller edge crossing the cut. And before I prove it, right, the intuition is right. The minimum spanning tree, because it's a spanning tree, it has to cross every cut, right? It has to go from one side to the other side. Well, because the minimum spanning tree, right, it better take the minimum way to cross it, right? Otherwise, it wouldn't be the minimum, okay? So that's the main idea, okay? So that's called, some people call it the greedy choice, some people call it the cut property, okay? So let's prove it. Well, the proof is essentially what I just said, okay? Consider some cut, right, S and V minus S, right, some set of nodes S, the rest of the nodes, and consider the smallest edge, right, the lightest weight edge crossing the cut. I want to show that that must be in some minimum spanning tree, okay? So the case I have to wonder is, okay, what happens if this edge is not in the minimum spanning tree? Can I reach some contradiction or somehow prove that that can't happen? Okay. So like I said, right? Let's say I have this cut, and somehow it turned out that this smallest edge is not in the minimum spanning tree. Then any idea like how I could argue that maybe I could get a smaller tree by including this minimum edge? Yeah. Yeah, exactly, right? That's the main idea, right? If somehow there's a worse edge crossing the cut, I add the smallest edge, it creates a loop, right? the loop must necessarily contain the other edge, right? Because I'm going from one side to the other. The loop must mean I have to go back to the other side, right? It's a loop. Well, then that means you're coming back from the other edge. And then the previous thing, right, told you, if I just remove that, it still remains a spanning tree. Okay? So exactly, that's why I showed you those two things. Right? So the proof goes like exactly what's your name? What Riley said, like we added edge, right? Let's say some edge, minimum edge, was not in the spanning tree. We added. It makes a loop. There must be another edge, right, that crosses the loop back. I know that must be a worse edge, right, because E was the smallest. So then I just like add that and remove it, stays a spanning tree, but now the tree just became better, right? So yeah, I mean, these are just words, but the proof is just here, right? Like if somehow the minimum spanning tree going from one side to the other did not add this edge, it must have some edge, right, going from one side to the other. I add this edge, it makes a loop, and I just remove that other edge. Okay, and it always like improves the tree, right? So that's all this is saying in words. Okay, so now let's get to how it helps us, right? So this is just some mathematical property of a minimum spanning tree, right? Like if I have a cut, the minimum edge should always be part of the minimum spanning tree. Okay. Now how do I use it to find the minimum spanning tree? Okay. Well, this property tells me, right, like somehow if I do this greedily, yeah. Yeah, so this is the graph, right? I'm saying this is what the graph looks like. That's the graph, right? And I'm saying, right, when I pick a minimum spanning tree, I must pick one way to cross the cut, right? Either this edge or that edge. And I'm saying, why would I pick the worst edge? I'm saying I would never pick the worst edge, because in my head, if I happen to pick the worst edge, I can just improve the tree, right, by adding this edge, making a loop, and removing the other edge in the loop. Yeah, so right, exactly, like you wouldn't have two edges crossing, because that would make a loop. But I'm saying it's anytime you have a cut, you can always just assume the minimum edge is part of the minimum spanning tree. Okay. Yeah, so the idea is like, right, I put the graph in two pieces, right? Somehow I've kind of dealt with each piece separately, right? So all I have to concern myself with is how to go across, right? Inside the piece, I don't care. And we'll see that in a bit. Like inside the piece, I don't care. I just need to figure out how to go across. And all this is saying is when I want to go across like a part that I'm at and the other side, I can always pretend I'm taking them in the smallest edge, okay? Okay. So essentially now this is going to inspire how to actually design design a way to construct the minimum spanning tree, okay? So I'll show you the algorithm in a bit, but the idea is we're going to build the MST one edge at a time, and at every time step, right, I have a connected part and I have the rest of the graph, right? And how do I pick the next edge? Well, I pick the best edge, smallest edge, going from the connected part to the rest of the part. So that's going to grow the spanning tree one vertex at a time, and at some point I'll be done, okay? So that's the main idea. Okay, so let me write it like not formally, like informally, and then later we'll see a more formal version that then you can argue about the running time. But essentially, right, we start with some vertex R, and I'll show you an example in a bit. That's our initial tree, right? It's empty. And then now how do I add to this tree? Well, I want to find, right, some way to connect the piece that I have with the rest of the graph. So then I just take the minimum edge, right, connecting the piece that I have to the rest of the graph, right, the safe edge, which is the smallest edge. And then I just keep doing this until everything is connected, okay? So, right, and like I said, this is a direct application of this like cut property or choice property, right? At every step, what cut are you considering? The cut that you're considering is from the piece that's connected to the rest of the graph that's not connected yet. Okay, so now let's see an example. Okay, so there's two examples. Okay, so the black the edges are my graph, okay, input graph. The green values are the weights, and these lines are how this algorithm works, okay? So initially, let's say my tree is just this node, okay? Now I want to say, okay, how do I connect this node to the rest of the graph, right? So that's a cut is like this, right? pretending I'm cutting right here. So what is the shortest way, the least weight edge that connects what I have to the rest? Oh, it's this. So I take this edge. Now I have two vertices, right? This in my tree, and I say, okay, what is the best way to connect this to the rest of the graph, right? So the cut is this. Well, is this a 5 edge, right? That's the smallest edge crossing this cut. That's the 5 edge. Now I have these 3 nodes, right, part of my tree, and I say, okay, now the cut is this. How do I connect these 3 nodes to the rest of the graph? I could take this choice, this choice, or this choice. Oh, well, this is the best choice, right? 7 is the smallest, so now I go this way. And now the cut is like, I have these 4 nodes on one side and the rest of the graph on the other side. What's the best way to connect them? It's this one, okay? And I keep going. It doesn't matter which node you start with as the root. So for instance, if you started here, the first edge will be this one, the second edge will be this one, and so on, okay? So you can try it on your own, but at least like how the algorithm works, does that make sense? At every step, I have a partial tree, and then the rest of the graph that has not been connected. And I say, how do I grow the tree by one edge? I just say, okay, what is the smallest edge connecting the tree that I have, the partial tree, to the rest of the graph? That's my cut, and I just take the smallest edge. Okay, so that's going to grow the tree one step at a time. So you're going to kind of, initially you have like, the small tree, and then the tree goes bigger and bigger and bigger, okay? And then it connects everything. Questions? Okay, all right, so how do we prove this, that this actually works? And essentially just like repeated application of this cut property. So let me just go through it, right? So essentially the lemma that or like the induction that we're proving is at every step you're always part of some MST, okay? That's the statement that we're proving. Okay, so the base case is true, right? The graph is empty. That's part of some MST. And I want to show that, okay, at some intermediate step, if I make one greedy choice, I will continue to be part of some MST. Okay? Like I said, right, like let's say I'm done the first step, I have this edge, right? How do I know that let's say that's part of the MST, I'm happy. How do I know the next choice I make is also part of the MST? And the proof is just the cut property, right? Let's say at some intermediate step, right, you have a cut. The cut is basically what you have connected to the rest of the graph. And the algorithm is picking the minimum edge. Right? By the greedy choice property, this is part of some minimum spanning tree, right? And if it wasn't part of the tree that you're tracking, you can just like swap some edges, right? You can always add that edge you picked and remove something else. And that will continue to be a minimum spanning tree, okay? So it's like a lot of words, but essentially it's the same thing, right? It's just saying if that edge that you picked was not part of the minimum spanning tree, you can change it so it becomes the minimum spanning tree, okay? But pictorially what's happening is like, okay, right, you're never going to pick this. You have to pick some edge crossing the cut, and it better be the smallest edge, okay? All right. Yeah, okay. Anyways, basically the main induction step is showing that every step you continue to be part of the minimum spanning tree, okay? That's all this is saying. All right. So now that we know, right, this algorithm works, it will give you a minimum spanning tree. How do I implement the algorithm, okay? So the naive way to implement it is, right, at every step, you check which edge can I add. So how do I check, right? I loop over the edges, and I say, okay, what is the smallest weight edge connecting the tree that I have to the rest of the graph that's unconnected? That takes OVE time, right? Because every step you're looping through all the edges. We're going to do much faster, okay? But this is the naive runtime. Does that make sense? So we're going to do faster, but just like why this naive runtime is VE. It's like I'm looping over every edge at every step, okay? All right, so then we're going to now, to actually implement the algorithm, we're going to use this priority queue again, okay? Just like in the Dijkstra's algorithm. And actually, there's like a connection between this algorithm and Dijkstra's algorithm. Because, right, what Dijkstra's algorithm needed is a way to go to the frontier really fast. And now the frontier is basically the tree. Whatever is the leaves of the tree that you have, that's the frontier. And you want a way to quickly reach the frontier and extend it, okay? So that's why the same algorithm almost as Dijkstra's algorithm works here, okay? So the way to keep track of like which edge is the next best edge to add, we're going to have this priority queue, right? So essentially, what is a priority queue? It's just a way to associate values to everything, okay? We'll call priority. essentially all the vertices will have infinite weight. Okay, so they're all bad, except the root you started with that has weight 0. And it's exactly almost the same as Dijkstra's algorithm. Okay, at every step you're going to extract the minimum, right? So you're going to, what is this, right? In the beginning, you're just going to pop out the root node, and then you need to update things, right? Update the frontier. But you're just going to do it by weight of the edges, not the path, okay, as in Dijkstra's algorithm. So what you do is you extract the minimum, and for each neighbor of this vertex you removed, you update that neighbor's key, okay, by the weight connecting. So essentially, the priority queue is keeping track of, for every vertex that's unconnected, what is the cheapest way for me to connect to the tree? Okay, that's essentially what it's keeping track of, okay? And of course, if I find the best vertex, right, that's the lightest weight edge. That's the smallest edge connecting the tree to everything else, right? So another way to say it is to simulate Prim's algorithm, you just need a way to say what is the next edge that I add to the tree. Well, the next edge better be the smallest weight edge connecting myself, the partial tree, to the rest of the graph. And that can be maintained by a priority queue, okay? That's all I'm saying. Like, the priority queue helps you find minimums fast, okay? Instead of doing a loop, priority queue will just tell me what the minimum is very fast. Okay, so that's why we're using this data structure. Any comments? Why this works? Questions? Yeah.
So like Kant can try to copy multiple edges at a time, but we just always chose like the minimal edge.
Exactly. Yeah, exactly, right? So another perspective of that is like, it's basically the cheapest way, right? So now we're going to say, okay, what is the cut that I care about? The cut I care about is the cut that's separating the tree that I have to the rest of the graph. And now on the cheapest edge, that's connecting myself, the partial tree, to the rest of the graph. And that edge is going to extend the tree by one edge. Okay, so that's essentially what we're doing. Yeah. Yes? Yeah, so that's why this cut property is important. Like, it's saying for any cut, the minimum spanning tree has to pick the minimum edge. Okay, so then the cuts that I'm going to write in the algorithm, what are the natural cuts I'm going to analyze? It's the cuts between the vertex, the partial tree, and the rest of the graph. So what we prove by induction is that at every step, you always maintain the fact that you're a subset of a minimum spanning tree. So yeah, try to look at the proof again later, and then you'll see like it doesn't matter which we start with. And actually, like another kind of consequence of the proof is, if I have unique edge weights, the minimum spanning tree is also unique. It's a non-trivial fact, right? Like, I just give you some complicated graph. I promise all the edge weights are different. That also proves that the tree is different. Or like, sorry, the tree is unique. But yeah, good question. Yeah.
So for this, if we just use a queue instead of a priority queue, isn't it like BFS?
It's kind of like a BFS. Yeah, it's like BFS, except the next kind of thing we expand has to be the minimum. That's all I'm saying. Yeah. So yeah, BFS, Dijkstra, right? Like Dijkstra and BFS are connected. This is connected to Dijkstra. So they're all kind of the same style of algorithm. Yeah, another way to think about it, right? All these algorithms so far we've talked about for a while now, they're growing the frontier, right, one at a time. Just what is the frontier is changing. Right here, the frontier is like the tree's boundary that's changing. Previously, it was like some circles around the source node. Okay. All right, so yeah, like I said, right, it's almost the same as Dijkstra, except we're not keeping track of the cheapest path connecting the source. There's no source here. Okay. Instead, we're keeping track of the cheapest way to connect the tree to the vertices. Okay, that's why, like, I'm not updating parent pointers, and there's no relaxation step, because I don't care about paths. I just care about the edge. Okay. Okay. So why did I have this? Okay. So let's just let's just see this example again. Right here, right, like for this node has value 0. Everything else has infinity, right, in the beginning. I pop the minimum, which is this node, and then I update the edges, right? So then this has 6, priority 6, this has priority 12. Then I find the minimum priority, right? Then I update the edges of this node. Then this node, right, gets its priority updated from 12 to 5. And then when I pop the minimum, this will get popped, okay? So essentially, it's saying one way to simulate this algorithm it's just by keeping track of the frontier of the tree. And essentially the only vertices that can ever be popped are the ones that are like connecting the frontier to themselves, right? Everything else that's down the line has priority infinity. I don't want to reach that yet. I just need to reach one more step, okay? So that's why this works. And now what is the writing time? It's almost the same as Dijkstra's, right? It's like, how many minimum pops am I doing? I'm doing n, right? Or if there's v nodes, I'm doing v. And how many decreased key operations I'm doing? Essentially, I'm doing at most twice per edge, okay? One time when the one side is popped, the other side is popped. So then it's kind of the same argument as Dijkstra's algorithm, right? There's different data structures that can do these operations, right? The simplest is the array, right? And another simplest is binary tree or binary heap. And there's this other thing called the Fibonacci heap, right, which is really powerful. And so for the sake of this class, you can think prim's running time is like if you implemented this using this Fibonacci heap. But right, if you were actually wanting to implement it, probably you just want to pick the binary heap. Fibonacci heap is like a crazy data structure. But you see, right now the running time is essentially e plus v log v. Well, not essentially. It is e plus v log v. It is much faster than v times e, right? Instead of multiplying, I'm adding these two things. So it's faster. And yeah, and it's pretty cool, right? Like when I told you this problem, right, there's exponentially many trees that could be possible. But we identify a greedy property, right, which said at every step, it's OK to make this greedy step. And by chaining together the steps, right, I have this entire tree. And every step you can find very fast using this priority queue. And that's it, right? We're just putting 2 and 2 together. OK, so that's it for Prim's algorithm. Next week, we're going to see another minimum spanning tree algorithm that's going to use the greedy property in a totally different way, just to let you see like the different ways you can exploit this greedy property. But yeah, that's it for this class. If you have any questions about your midterm or you haven't picked it up yet, I have it, so I can stay here for like 20 more minutes. Okay. Oh yeah.
So last class we pretty much go through the proof of Dijkstra's, but like I don't remember if you said that, but is that level of proof expected to show up in the exam?
No.
Okay.
Yeah, so the exam is mostly like, I give you a problem, how do I use the algorithm that I know to solve the problem, right?
Okay.
Kind of like homework, like, I have this graph with some property, find the shortest path. And maybe it's like, oh, I add a super node and then run Dijkstra from that super node.
Okay.
Yeah, it's not like, it's more like using the algorithms. That's why going to discussions is important, because we solve problems in discussion.
Okay.
Yeah.
And also one question is, so if we do that, like midterm makeup, like submit into
Yeah.
the grade school,
Yeah.
so eventually it just kind of prevents us from failing.
Oh yeah, for sure, yeah. It's more like, exactly, like, you definitely won't fail if you do that. And it might help you like get bumped up to a higher letter grade too later on.
Okay,
Yeah.
so like guarantee not failing, just even if we do pretty bad.
Yeah, for sure, yeah.
Thank you.
Yeah.
If I wanted to like ask for a reread on one of the questions, you would only be or I can only ask you for question 3s.
You can ask me for any question, yeah.
Or any question?
Yeah.
Can I ask you right now? Or?
Sure.
It was the first question.
Okay.
I got a 0 out of 10 because I mentioned like merge sort.
Yeah.
I thought that the algorithm would end up working overall.
Yeah, but you see, like, okay, like this is almost impossible to grade, right? Look, you're giving me this like super long explanation.
Yeah.
And it's like so complicated what you're writing. So let me, I can't do this on the spot, so let me take it home and
Okay.
I can think about it.
Good.
But I can send you an email if something changes, okay?
Thank you.
Yeah. Yeah.
Okay.
Oh yeah, what's your name? What's your last name? If I sorted it, but it's not sorted. Okay, Jackie, I think you're unlucky towards the bottom half of the pile.
The one in the back.
Yeah. Oh, are you in the back? Oh, okay. I thought you saw the name on the back. Damn. Wait, hold on.
It is though. Oh, this is mine.
Okay, yeah, feel free to take it. Oh my god. That would be crazy. Oh yeah, no, it's not. There you go.
Thank you.
Yeah.
Have a good one.
Yeah.
We want to ask, is it possible that we can write like recommendation letter for us?
Not till the end of the semester, sorry.
Oh yeah,
Yeah.
but because like some of the graduate school deadline is before the end.
Oh yeah.
Yeah.
Yeah, it's just like my personal policy that I wait until the end.
Okay.
But I would say like, did you guys take a grad class before?
No.
No, or like an advanced class or something, like advanced undergrad class in CS? You know, like what high number? Yeah, it's
a
just
lot of other classes.
yeah. So you should ask the person that you got a good grade with, right? Because then they submit by like December, right?
So I got some schools that are due like next year, so is it possible that if I
Oh
get
yeah,
an A
sure,
in this
sure,
class,
yeah,
I
yeah,
can pass?
yeah, for sure, yeah, yeah.
Yeah, thank you.
Yeah. See ya.
I could go to discussion segment.
What's your name?
Yashvi.
Ashvi. Yeah, sorry, I can parallel work. So sorry, what would
Yeah. Oh, okay.
I can do parallel work? Yashvi. Or you know, we can hold off on a bit. Let me just quickly find Yashvi's test. Damn. Everybody's at the back. Good. Okay. Unlucky. Unlucky. Okay, we'll go and go from the back. Oh, there you go. Yep. Yeah, so it's.
So for problem 1, I got a point off for not like.
Oh, okay. Yeah, I can give you a point back. That's
Yeah,
that's
'cause-
simple.
yeah,
Okay.
because all of us have the
Yeah,
same
I have
because
the
we were
same
discussing that we
Okay.
really did.
All right. Yeah, just if you have any concerns, if not, I'll take it home and update it later. But
Okay. Yeah.
is there anything else?
Go for it.
Yeah. Okay.
With the third one, I
Okay.
posted on Piazza and you told me to.
Oh yeah, because your thing was like unreadable.
Oh, sorry. Yeah, that was the third one. I did I did the method from class, you know,
Yeah.
the fraction m/2 thing, and then
Yeah, I guess.
I also have the explanation.
I have a similar thing. I know I didn't I know this is not right and I didn't simplify it out, but I feel like I should at least get a point or two for the explanation because I did conceptually have it.
Hold on. Let me take one at a time. It should be take a K type if this is done. Yeah, this is not correct, right? Like you're not exploiting anything about the special structure, right? The structure that if you read the solution, right, the structure we're exploiting is for the algorithm, right? You pick one element from each, sort that, and then sort inside, right?
Yeah, so I said divide like the m parts first and
Oh,
then
inside.
within each
Oh,
part,
I see. Okay, I see what you're saying. M parts.
and then within each part.
All right, let me take it home and then kind of think about it. Okay.
Okay.
Yeah,
okay.
but that's it, right? That's
yeah,
all.
the
Question.
B and C
Okay.
part of question 3
Okay.
and then question 1.
Okay. Yeah, yeah. Question 1 I remember, so let me put it here. All right.
Thank
Alright,
you.
My answer for C is
And have since we reach a subsequence. Yeah. So. Right. So like. But you haven't said like what is the running time for sorting every subsequence, and then like the fact is you can do much better than n log n for this special structure, right?
Okay.
It's yeah, and this is like omega of m factorial, right? That's
yeah.
that's a lot. But the part B, yeah,
I think I know the math for my part B is not
okay.
all the way.
Yeah, so the way I graded part B was like, first was the explanation, and the second was just like, could you use this thing that I told you? But yeah, I'll take a look again.
Okay.
But at least for the first problem, I can give you something.
Sure. Sounds good.
Yeah. Okay, all right.
We just wanted to pick up the intern.
Okay, what's your name?
Grace.
Grace, okay. Hold on 1 second. Grace. Grace. Yeah, do that for sure. If you do that, then that shows me that you're working hard and that we can help you out later. That's all that is.
It was kind of disappointing because I figured out how to I knew how to explain some things that were on the practice test and the homeworks to other people.
Yeah.
And then it just happened to be that part was not what I had on my.
Yeah, that's why that's difficult with a test. It's unfortunate, but there's no way around a test. And some people, right, like it's like you only have such limited time. So it's not the best judge of your knowledge. That's why I'm asking people to that's why I'm asking people to redo this thing, right, on Gradescope, where you redo the test and like write in your words. And then right, if you do well on the second and the final then if I see improvement, then I can pretend that this test didn't happen. That's like I'm not trying to screw over anyone. So if you do well in the next two things, I can take that into account heavily and give you a much better grade. Okay, does that make sense? I mean, I can't say anything concrete, but it's just more like if you do well on the second thing, and I notice that, let's say you're borderline and you did this extra thing, I'll definitely bump you up. Okay. Yeah.
Just kind of because you did mention it's an unfortunate thing that happens where it's just like the one thing that I don't cover on the thing ends up being the one thing that gets tested.
Right.
This has been something that's been going on to me for years.
I see.
And at this point, I don't know what would be the best way to counter this because, quite frankly, I've had enough of being unlucky.
I see. So yeah, so I think next time, right, what I'll do is I'll include more practice, and this test was short, right? It was like you either get it or you don't. So next time I'll have more like multi-part problems, so that at least like there's a way to build up. So then it's not just like one problem. So I can definitely do more of that. But I mean, I know you come to class and like I know you're doing well on the homework. So I would say do this extra thing, right? And then that can we can use that to help you. And if you notice, like, if we graded something wrong, let's also let us know,
No, I know that I did not do well at all. I'm kind of lucky that I ended up in the lower quartile in the first place.
Yeah.
I didn't realize that we could keep our midterm.
Oh, okay.
I just wonder if I can get it. My name is Nathaniel Kim.
I see. What are you going to do with it?
I just wanted to review it.
I see. I was just kidding.
Gradescope.
I was kidding.
I know sent you an email, but for some reason it kept saying it was getting rejected.
Oh, that means you probably sent it to the wrong address.
Oh.
So did you send it to me? So you want to check?
On the syllabus.
Okay, so that's your work. You want to check right now which email you're using? Oh.